I'm going to work out a few examples now to show how to perform continuous time convolution. So let's begin with the example where we're supposed to convolve the signal x of t, which is u of t plus 3, with h of t, which is e raised to minus t times u of t. Okay. So we want to figure out x of t convolved with h of t, which is given by integral minus infinity to plus infinity x of tau h of t minus tau theta. And we're going to call this signal as an intermediate signal called w sub t of tau. Okay. So we begin by first thinking of x of t and h of t as signals where the independent variable is tau. So let's begin with x of tau, which is given by u of tau plus 3, and h of tau, which is e raised to minus tau u of tau. Okay. So often it's very useful to actually draw or roughly sketch these signals x of tau, h of tau, and h of t minus tau, so on and so forth. And when you perform the convolution, it's also a good idea to get a rough feel for how y of t looks. Okay, so let's begin with sketching x of tau. So x of tau is a unit step function shifted to the left by 3 units. Right, it's u of tau plus 3. And h of tau is a signal. Maybe I should draw them to be at the same height because they're both 1 at t equal to 0. So this is e raised to minus tau, and this signal is 0 for all values of tau less than 0, and it's e raised to minus tau for all values of tau greater than 0. So it's really important to understand that now we are thinking of tau as the independent variable. Okay. Okay. Then what we do is we flip h of tau around the y-axis to form the signal h of minus tau. Okay. So what happens is we have h of, maybe I will draw it here. So h of minus tau is a signal which is just a flipped version of h of tau. But mathematically this signal can be obtained by replacing tau by minus tau. So this function actually becomes e raised to tau, and this function is 0 for all values of tau greater than 0. Oops, I better be careful. I have to align the 0 with this 0. Yeah. Okay, so this is h of minus tau. So then the next step is to actually shift h of minus tau by t units to the right. In order for you to figure out y of t, what we need to do is we need to shift h of minus tau by t units, and then multiply h of t minus tau with x of tau, which is the intermediate signal w, and then integrate that signal for all values of tau from minus infinity to plus infinity, and that will give you the answer for y of t. Okay. Now I keep saying shifted to the right by t, but when t is negative, clearly this means that you want to shift to the left instead of shift to the right. Okay. Now one of the main difficulties in convolution, or one of the important things to keep in mind, is that when you shift h of minus tau by t and then you take the product of h of t minus tau and x of tau, the resulting function w sub t of tau may actually have a different mathematical expression or a different functional form for different values of t. Okay, so one of the important things is to be able to figure out for what ranges of t the expression for w of t will, or w of tau, I'm sorry, will look the same, and try to compute y of tau over these different ranges separately. Okay, I'll illustrate this with an example. So let's look at the signal h of t minus tau. What is h of t minus tau? H of t minus tau is obtained, remember this is e raised to tau, is obtained by shifting this by t. To the right. But when t is large and negative, h of t minus tau looks like this. Right? So what happens is we have shifted it by the absolute value of t to the left. So the 0 actually now starts, or this 0 now goes to t. And this function becomes e raised to, we have to replace tau by tau minus t. Okay. So this is the case when t is less than minus 3. Well, what's magical about minus 3? Well, what's magical about minus 3 is this. If t is less than minus 3, h of t minus tau and x of tau will not overlap at all for any value of t, and what we will end up with is this will give us an intermediate signal wt of tau, which is 0 for all values of tau. Right? Essentially what's happening is I am multiplying this signal and this signal. Okay. However, if t is greater than minus 3, what's going to happen is it's going to look, h of t minus tau is going to look like this. So t would be somewhere here. Minus 3 is here, t is here, and I have the function tau minus t. Again, I got this tau minus t because we are shifting h of minus t by t units to the right, which means I'm replacing tau by tau minus t. Okay. So in this picture t is still negative, but it's just greater than negative minus 3. Okay. If t is positive, it's just still going to look the same way. So if t is positive, it's still going to look like this. Right? So whenever t is greater than minus 3, when I take the product of x of tau and h of t minus tau, what I'm going to end up with is something which looks like this. It's going to be 0 for all values of t less than minus 3 because x of tau is 0. And it's going to be 0 for all values of tau greater than t because h of t minus tau is 0 for all values of tau greater than t. Remember, the axis is tau here, or the independent variable is tau. Okay, so this is how w sub t of tau looks for all values of t greater than minus 3. Okay, when I say this is how it looks, what I mean is this: the functional form of this looks the same. It is always going to exist between minus 3 and t, and this is going to be e raised to tau minus t. Okay, Clearly, as t changes, this point is going to move to the right, and you're going to see more and more of this function e raised to tau minus t. Okay, so we can write this mathematically as wt of tau is e raised to tau minus t for all values of tau between -3 and t, and it's 0 for other values of tau, either when tau is from -infinity to -3 or from t to infinity. Okay, now that we have determined the function of the form of w sub t of tau, y of t can be obtained by simply integrating wt of tau d tau from -infinity to +infinity. Now, so what is this? For values of t less than -3, this is clearly going to be 0 because we are integrating 0. But for values of t greater than -3, this will end up being integral -infinity to +infinity of this function. Okay, but you can see that this function is 0 except when tau takes this range of values. So this function can be written as -3 to t e raised to tau minus t d tau for all values of t greater than -3. Okay, it's really important to understand that this is a range for t, whereas this integral is with respect to tau. Okay, essentially what we're doing is to determine y of t at every value of t, we actually have to perform an integral with respect to tau. So this integral, of course, is e raised to tau minus t between the limits -3 to t, which gives us what does it give us? It gives us 1 for the upper limit minus e raised to -3 minus t. Okay. Yeah. If we were to roughly sketch this function y of t, how's this function going to look? Well, until t equal to -3, this function is 0. Then for values of t greater than -3, you can see what happens is this function is increasing like this. It's 1 minus an exponential, so it's kind of increasing like this. And when t is infinity, this goes to 1. So this is 1. Okay, roughly that's how this function looks. All right, let's work out maybe I'll stop the video here and then work out the next example in the next video.